Welcome to 3x3 constant coefficient homogeneous system examples. So for example, let's find the general solution to the equation y prime equals ay, where A is the matrix, first row 2, 0, 5, second row 0, negative 3, 0, and last row 0, 4, 3. So again, the first thing we need to do is find the eigenvalues. So we are looking for where the determinant of the matrix 2 minus lambda, 0, 5, 0, negative 3 minus lambda, 0, 0, 4, 3 minus lambda. We are looking for where this determinant is equal to 0. This determinant, we have 2 minus lambda times negative 3 minus lambda times 3 minus lambda. Then we would have for our second forwards diagonal plus 0. For our last diagonal, we have plus 5 times 0 times 4, so plus another 0. Then for our backwards diagonals, we'd have minus 2 minus lambda times 0 times 4, so there's a minus 0. Then minus 0 again, and for our last diagonal, minus 0. So essentially, we have 2 minus lambda times negative 3 minus lambda times 3 minus lambda equals 0. And so we can pick lambda 1 equal to 2, lambda 2 equal to negative 3, and lambda 3 equal to positive 3 for our eigenvalues. Next up, we need to find the eigenvectors. So for lambda 1 equaling 2, we are looking at the augmented matrix. 2 minus 2, 0, 5, followed by 0, negative 3 minus 2, 0, followed by 0, 4, 3 minus 2, and then the augmentation is just the 0 vector. So this is equivalent to 0, 0, 5, 0, 0, negative 5, 0, 0, and then we have 0, 4, 1, 0. So from here, this results with us getting our psi2 is 0, as is psi3. Like psi1 is free. And so we can just pick our vector psi1 to be first position is 1, and then second and third row are both 0. For lambda 2 equaling negative 3, we are looking at the augmented matrix, the original matrix being 2 minus negative 3, 0, 5. Second matrix being 0, negative 3 minus negative 3, 0. Last row 0, 4, 3 minus negative 3. And then the augmentation is just the 0 vector. So we are looking at 5, 0, 5, 0 for the first row, 0, 0, 0, 0 for our second row, and 0, 4, 6, 0 for our last row. We do have a free variable. We can write both Xi1 and Xi2 in terms of Xi3. So we have Xi1 should be negative Xi3, and 2 times Xi2 should be equal to negative 3 times Xi3. So if we pick Xi3 to be equal to 2, then we have Xi1 would be negative 2, and Xi2 should be negative 3. And so we wind up with the vector. I need to give myself a little more space. All right, we wind up with the vector. Our Xi2 is, we had negative 2, negative 3, 2. Then we have to find one more eigenvector. Lambda 3 was equal to 3. The augmented matrix we are looking at, we had 2 minus 3, 0, 5, followed by 0, negative 3 minus 3, 0. Followed by 0, 4, 3 minus 3. Again, we're just taking the original matrix and just subtracting lambda off the diagonal. Then our augmentation is the 0 vector. So we are looking at negative 1, 0, 5, 0 for our first row, 0, negative 6, 0, 0 for our second row, and 0, 4, 0, 0 for our last row. We have the Xi2 has to be equal to 0, and our only other restriction is that Xi1 is equal to 5 times Xi3. So we can pick Xi3 to be equal to 1. That means Xi1 is 5. And we have our vector. We have our vector Xi3 should be equal to 5, 0, 1. Putting this all together, we wind up getting our general solution. Y is equal to C1 times our first eigenvector was just 1, 0, 0. That corresponded to lambda 1 equaling 2. So we have C1 times 1, 0, 0 times e to the 2t plus C2 times our second eigenvector was negative 2, negative 3, 2. That corresponded to lambda equaling negative 3. So we have negative 2, negative 3, 2, and that's times e to the negative 3t. Then we have plus C3 times 5, 0, 1. That corresponded to lambda equaling 3. So then multiplied by e to the 3t. So this is one example of the 3 by 3 case. Let's go ahead and do one more example. Let's find the general solution to y prime equals a times y, where a is the 3 by 3 matrix. First row 5, 2, 3. Second row 0, negative 1, 0. and last row 0, 0, -1. So again, the first thing we need to do is find the eigenvalues. So we are looking at the determinant of 5 minus lambda, 2, 3, 0, -1 minus lambda, 0, 0, 0, -1 minus lambda. Looking for this being equal to 0. We have a triangular matrix here. The determinant is just the product along the diagonal. We wind up getting 5 minus lambda times -1 minus lambda times -1 minus lambda. You could always check the rest if you wanted. We have plus 0 for our remaining two forwards diagonals. And we have -0, -0, and -0 for our three backwards diagonals. That should all equal 0. So we are looking at 5 minus lambda times -1 minus lambda squared is equal to 0. So we can take lambda 1 to be equal to 5, and lambda 2 and lambda 3 are equal, and they can be equal to -1. So here we have our eigenvalues. Next up, we need to find our eigenvectors. So we have for lambda 1 equaling 5, we are looking at the augmented matrix. We have 5 minus 5, 2, and 3 for our top row, and then 0, -1 minus 5, 0 for our second row, and then 0, 0, -1 minus 5 for our last row. And then the augmentation is just the 0 vector. So we are looking at 0, 2, 3, 0 for the first row, 0, -6, 0, 0 for the second row, and 0, 0, -6, 0 for the last row. We have therefore the xi2 is equal to 0 and xi3 is equal to 0, but xi1 is free. So we will go ahead and pick our vector to be xi1 equals 1, 0, 0. For lambda 2 equaling lambda 3 equaling -1, we are looking at 5 minus -1 followed by 2, 3. Then we have 0, -1 minus -1, 0, and 0, 0, -1 minus -1, and then our augmentation is just the 0 vector. This becomes 6, 2, 3, 0 for the first row, 0, 0, 0, 0 for the second row, and 0, 0, 0, 0 for the third row. So we have two free positions. I'm going to set xi1 and xi3 to be free. And we have the xi2 is equal to, we would have -3 times xi1 minus 3/2 times xi3. So it's kind of up to you how you do this. You can pick psi1 to be 0 and psi3 to be something else, and then do the other way around, or we can just write our vector. We would have psi1, and then we would have negative 3 psi1 minus 3 halves psi3, and then psi3. We can split this as psi1, negative 3 times psi1, 0, plus 0, negative 3 halves times psi3 and psi3. So for this first vector, if we just pick psi3 e to be 0 and psi1 to be 1, then we get, I'm going to say our vector psi2 is just 1, negative 3, 0. If we pick psi1 to be 0, I'm going to pick my psi3 to actually be 2. Then we wind up getting the our psi2 would have to be just negative 3. And so our vector psi3 will be 0, negative 3, 2. Of course, you could have picked those completely without actually writing out this split, but this split kind of shows us what we're working with. You obviously could have just pulled out the psi1 from the first vector. We would have immediately had 1, negative 3, 0. If you pulled out the psi3 from our second vector, you would have had 0, negative 3 halves, 1. I just scaled that by 2. At this point, we have all of our eigenvectors. We do have the case of n linearly independent eigenvectors, even though we did have a repeated eigenvalue. We can go ahead and find our general solution. Y will be equal to C1 times our first eigenvector was 1, 0, 0. And that corresponded to lambda equaling 5. So we will have C1 times 1, 0, 0 times e to the 5t plus C2 times our second eigenvector was 1, negative 3, 0. This corresponded to lambda equaling negative 1. So we have 1, negative 3, 0 times e to the negative t. And then our last eigenvector, we have 0, negative 3, 2. Sorry, we should have a plus C3 times 0, negative 3, 2, again, times e to the negative t. So this is a case where we did have a repeated eigenvalue, but we still had a basis of eigenvectors. And so we were able to still write our general solution in this format we've learned so far. All right, so that is what we do if we have real eigenvalues with n linearly independent